Thank you, everyone. Thank you, Valerie, for that really nice introduction. Thank you, everyone, for your attention today. And I'm very grateful and honored to be speaking today and to give the keynote at this interdisciplinary conference. I'm particularly feeling good about being invited to speak at an interdisciplinary conference because every time I've done an interdisciplinary project, it was terrifying at the beginning, and then there was always some setback that was very scary. And so one of the things that I wanted to make sure to talk about today is how it's really important to turn setbacks into opportunities and how the most exciting findings can come out of that. So I need to start by explaining the title of my talk, which is Yes and. And so this is borrowed from the improv comedy world, and I first learned about this from one of my idols, Tina Fey. And so I have an excerpt from her book to tell you about the yes and approach to improv, which I think is extremely useful for interdisciplinary collaborations in science. So she said,
yes and.
You want to plug it in?
You want to plug it in.
That usually helps.
There we go. Turn the power strip on.
Okay. So, and this is an excerpt from Tina Fey's book, Bossy Pants. The second rule of improvisation is not only to say yes, but yes and. You are supposed to agree and then add something of your own. If I start a scene with, I can't believe it's so hot in here, and you just say, yeah, we're kind of at a standstill. But if I say, I can't believe it's so hot in here, and you say, what did you expect? We're in hell. Or if I say, I can't believe it's so hot in here, and you say, yes, this can't be good for the wax figures. Or if I say, I can't believe it's so hot in here, and you say, I told you we shouldn't have crawled into this dog's mouth. Now we're getting somewhere. To me, yes and means don't be afraid to contribute. It's your responsibility to contribute. Always make sure you're adding something to the discussion. Your initiations are worthwhile. And then she goes on to say, there are no mistakes, only opportunities. If I start a scene as what I think is very clearly a cop riding a bicycle, but you think I'm a hamster in a hamster wheel, guess what? Now I'm a hamster in a hamster wheel. I'm not going to stop everything to explain that it was really supposed to be a bike. Who knows? Maybe I'll end up being a police hamster who's been put on hamster wheel duty because I'm too much of a loose cannon in the field. In improv, there are no mistakes, only beautiful, happy accidents. And many of the world's greatest discoveries have been by accident. I mean, look at the Reese's Peanut Butter Cup or Botox. Okay, so I think you can clearly see how applicable these lessons are to research. As long as you keep in mind the advice of another almost equally influential person, Dr. Louis Pasteur, who said famously, fortune favors the prepared mind. And so to me, what this means is that research and happy accidents are really not an accident. You have to work to take advantage of accidents and make sure that they turn into something fruitful. And in interdisciplinary collaborations, you can't just say, I'm going to do my discipline, you do your discipline, and we'll mash them together and something great will come out. Each side has to work hard to understand what the other one is doing. It doesn't make sense to try to become an expert in what the other side is doing, but you have to meet them where they are and learn their language in order for something productive to come out of it. And so what I want to talk about today is a few examples about how I've tried to do that and how it did turn out some really interesting things came out of it by working with people from very different disciplines. So a great example of an interdisciplinary project that has become its own field is tissue engineering. So how many people have seen this image before of a human ear grown in the back of a mouse? Yeah, so this experiment was really the start of the field of tissue engineering. And that field is where you take cells from a patient, so the building blocks of life that we're all made of, and try to grow a tissue in order to repair some catastrophic damage in that person. So in this particular experiment, what the engineers and the clinicians and the biologists were trying to solve is the problem of microtia, a congenital disorder in which sometimes people are born without an ear. And the problem is not necessarily hearing, because, although the ear does direct sound into the ear canal, the issues with these patients is really more psychological and how it feels to go through life with people staring at your lack of an ear. And so this was really, this is really something that they just needed the shape of the ear construct and the mechanical properties to look like an ear in order to solve this problem. And so I want to talk about today how I had the opportunity to go and work for Yilin Cao, who was the lead researcher when he was a postdoc who worked on this project, and he started his own lab in Shanghai. So tissue engineering is the idea that you have a patient with some catastrophic injury, they're not healing them, they have some tissue injury that's not healing itself. You would take the cells from the patient, from probably a stem cell that might have the ability to differentiate into other cells of your body. You combine it with a biomaterial, so any biomaterial, a biomaterial is just something that you make that is able to interact with the body and coax your cells into behaving normally. You might grow it in a bioreactor in the lab, so you might apply some mechanical forces or some special cocktail of drugs or stimuli in order to get it to grow, and then you implant it back into the patient. So the way that I got involved in tissue engineering was during my PhD. So in my PhD research, I was studying polyvinyl alcohol hydrogels, or PVA hydrogels. So hydrogel is basically Jell-O, so it's like you have plastics that are so swollen with water that they have this sponge-like quality, but it's not a sponge where water comes out, it's more like it's a swollen, fluid-like kind of solid, like Jell-O. So Jell-O is a hydrogel. So PVA hydrogels are just like Jell-O, except they're mechanically stronger, so they are an excellent candidate for replacing damaged cartilage in your knee. So how many people in this room know somebody with knee pain? Yeah, it's extremely common. And so people have been working for a long time to try to make a material that could take over the mechanical limitations that damaged cartilage has in your knee. And in fact, in 1973, it was first proposed by my advisor's advisor, Merrill, that polyvinyl alcohol hydrogels could be used for synthetic articular cartilage replacement. So you can imagine how 30 years later, it was a little frustrating to still be working on this very same project. But this was the project that was given to me, and when I was first starting out, of course, I didn't know any better. So my PhD was basically focused on optimization of the properties to mimic cartilage. So I spent a lot of time working on the mechanical properties, lubrication, which is really important for cartilage so that your knee, slides fluidly without locking, and making sure that fluid flows the way that it's supposed to through your knee. There was just one problem. I started this research in 2004 when I was still an undergrad, actually, and in 2006, this paper came out in a German journal called Neuroinflammation. Do not speak German. But luckily, German is really just messed up English, so I was able to kind of read this article, and I had a friend who spoke German who helped me. So what this article showed was that they took PVA hydrogels, the very material that I was working on, and they implanted it in human knees. And that's a picture at the bottom of a hydrogel, which is the German word for hydrogel, implanted into human cartilage. And it worked initially, but after 12 months, it completely failed. All of the hydrogel shrank away from the surrounding tissue, and now you just had a bigger hole with a foreign material stuck in the middle of it. So it was a massive failure, and this was the subject of my PhD research. So I was freaking out, as you might imagine, and I considered this a pretty major setback. But that same year, a paper was published by the Shanghai Key Tissue Engineering Laboratory. And this is the same lab that Yilin Cao had published 20 years prior about the ear on the back of the mouse, which is just cartilage, a different type of cartilage though. So they showed that they knew how to grow cartilage that had perfect integration with surrounding tissue. But the catch was it had terrible mechanical properties. And the mechanical properties are really important for cartilage because you actually put 18 times your body weight on your knee cartilage every day just walking around. So if you're able to get excellent integration but you have terrible mechanical properties, that's also a catastrophic failure, okay? So I thought, what if we just combine what I've been doing with what they've been doing? So they have great integration, I have great mechanical properties, and that will solve our problems. So I impulsively emailed Yilin Sao in 2008 and said, I'm an American graduate student, I'm working on cartilage, can I come work for you for free for a few months? And he said yes. So I first went over in 2008 for a month. We discussed possible projects. I met all my new lab mates, I learned what they had available, and I learned Chinese. And actually, I had been learning Chinese at Drexel prior to that as a hobby because a friend of mine made me a bet that I couldn't learn Chinese because my Western mind was too simple to learn such a complicated language. And I was like, well, we will see about that. So I started learning Chinese, and then I learned about this group, and I was like, I should go to China, so that's what I did. But actually, I had so much, I went over to China for 2 months just to learn Chinese before going to the lab for 1 month, so I was there for 3 months in 2008. And I had a lot of free time on my hands, you know, just living alone in China. And so I wrote a paragraph about myself and my research, translated it to Chinese, and then had my colleagues at Drexel who were Chinese edit it for grammar. And then I just memorized it because I figured on the off chance that somebody in China asks me about my research, I will be able to just recite this paragraph and they will understand what my research was. So when I got to the lab in Shanghai, you know, I was like, ni hao, you know, basic, extremely basic Chinese. It was not very impressive. But I could like say, hello, my name is Kara, you know, so they're all like, isn't this adorable, you know. And then, so they're introducing me to the rest of the lab, and they're like, Kara, would you like to say a little bit about yourself in Chinese? And I was like, oh my God, it's happened. This is my opportunity to recite my paragraph. I can't believe this opportunity has actually presented itself. So I recited the paragraph that I had been practicing because I had so much free time living in China. And when I finished, everyone, their jaws were like wide open, and I thought that they didn't understand anything that I said because they were so silent and just staring at me. And then they like erupted into applause and started cheering. And it was a great feeling. And they were like, you need to come back to Shanghai for way longer than 1 month because we're going to do great things together. So I went back to Drexel and I wrote a grant to the NSF and received it, so $15,000 just me to spend for 4 months in Shanghai, which is sort of a lot of money for an American grad student to spend in Shanghai in 4 months. So I had a great time, as you might imagine. But what I ended up doing, the nice thing about having that year in between meeting the lab and going back a year later, was I really planned down to the day what I was going to do in my experiments when I went back for that second time. And so that was critical for actually getting something done because 4 months is not a lot of time to finish a research project. So what we focused on was enhancing integration between cartilage and the material that I made because mechanical properties were great, it was just integration. So to do that, what we did was we wrapped my materials, the hydrogels, in these fibers that we then seeded with cartilage cells. And that was really just a model to see, could we get cartilage cells in the vicinity to see if we could get them to grow into the material. So this is what it looked like. That's a very fancy schematic of the fibers wrapped around the hydrogel. That's a picture of what it looked like. And the innovation was to release a growth factor, a protein from the scaffold, or from my hydrogel. So I designed my hydrogel so that they would slowly release this protein called IGF-1, which cartilage cells are known to migrate towards. So I figured if I could get it to slowly release over several weeks, it would keep enticing the cells to crawl into the material and then hopefully just lock it in place. So the variables that we looked at was a high dose of IGF-1, a low dose of IGF-1, and then our controls were no IGF-1, and then a really strong control was no cells at all, so that was just to see what would happen without any cells. And then we implanted it subcutaneously in nude mice for 6 weeks. As I was looking at my slides this morning, it occurred to me that many of you may not know what a nude mouse is, and it made me realize that that's a silly term for a mouse. But that's actually a colloquial, it's like almost like scientific slang for this mouse that doesn't have an adaptive immune system. It's So they have their regular immune system, but they don't have the ability to reject like a foreign implant or something. So for example, if you're transplanting an organ into a person, they typically need to suppress their immune system so they don't reject the organ. So the same thing happens when you're doing animal models that involve cells. You can't just put another animal's cells into it, you have to suppress their immune system. So these mice are called nude mice because they don't have any hair as a weird byproduct of the genetic mutation that eliminates their immune system. So they're called nude mice. Okay. Actually, in the past, I've had a funny cartoon of Mickey Mouse with like a black box censoring it, but I thought we'll keep it professional. Okay. So the results were really cool. So what we found is that the IGF-1 really did enhance integration with the surrounding tissue. So what you're looking at here is the hydrogel in the middle, and on the outside, this is the control, so there's no cartilage. But the B, C, and D have cartilage growing on the outside of the hydrogel. And with in B, where there's no protein, you can see that there's zero integration with the surrounding tissue. And in fact, when I first took the sample, I squeezed it, and the hydrogel went flying across the room because it was just like fluid, just a pew. But when there was IGF-1 involved, there was some tight integration, and the integration increased with the dose of IGF-1. And in fact, I tried to measure this. I tried to measure the force that it would take to break that integration by gluing chopsticks to either side of the material and then pulling carefully so I could measure the force that it would take to break that bond between the cartilage and the hydrogel. And it actually worked to a certain extent, but I ruined so many samples trying to do this that I didn't get enough data to get it in the publication. But I thought this was pretty fun because they really do use chopsticks for everything over there. They would like pick up, they use pipettes as sterile chopsticks that they pick things up. It's crazy. Okay. So that was my introduction to tissue engineering. And actually it's really exciting because right now, tissue engineered products are making it into patients. And when I started this 10 years ago, I thought that they were never going to make it into patients. And I would give a presentation at a conference like this, and somebody would say, "That's never going to make it into patients. Why are we even working on this?" And there was a lot of haters out there. Well, guess what? They're in patients now. It's so exciting. It's really saving lives already. So this is an example of a trachea. Blood vessels have been implanted, and nasal cartilage reconstruction, among others. So tissue engineering is an example of interdisciplinary collaboration between engineers, biologists, and physicians that is like a crazy idea that's now starting to work. But there's one example of a tissue engineered product that worked, but not at all the way that the engineers expected it to. So dermagraft is a material that was designed, it's a product that was designed for chronic wounds, like diabetic ulcers, which if I have time, I'll talk about a little bit at the end of my talk today. So dermagraft is actually a biomaterial, and the cell that they chose to seed on the biomaterial is human foreskin fibroblasts. So this innovation was that there's foreskin from babies, which heal themselves very well, that's being thrown out all the time, all over the place. So let's take those cells, which are fibroblasts, which are the same things, that's skin, and put it on this biomaterial, grow it into skin, and use it to patch a diabetic ulcer that's not healing like it should be. And so it turns out this actually works. It's not 100%, it's not super effective, which is why there's still a need to work on diabetic ulcers, but it was way better than all of the other treatments that have ever been tried for diabetic ulcers. So someone had the idea at one point to fluorescently label those cells so that you could tell what happened to them. So you make this foreskin, you basically take baby foreskin and you put it on somebody's diabetic ulcer, and then what happens to the cells, because if you don't know what's going on, it's hard to improve a product, right? So these people tracked the cells, and they found out that within days, the cells were completely gone. So it didn't turn into skin like they thought it would. The cells completely died. But it still worked. So how did it still work to promote healing of wounds that very rarely heal on their own when the cells were dying in a couple of days? And it turns out it was stimulating the patient's immune systems to mount their own healing response. And so that sparked the field of regenerative medicine. And this is what I'm really excited about now. That's the idea that your body heals itself correctly and sometimes perfectly all the time. And if we can figure out how it is that your body does that, can we make biomaterials that elicit a regenerative healing response? So that instead of having to go through that crazy process of taking cells, growing it on a scaffold, putting some mechanical forces on it and putting it back in the patient, because that's kind of a regulatory nightmare. Here at Drexel, I was taught to be very translational and to think about how we're actually going to be manufacturing products. That's a manufacturing nightmare, that strategy. And it turns out you might not need to do it. So I want to tell a story about how I really started thinking about this, that my grad students have heard a lot because it was such an impactful conversation that I had. When I was studying, I started my postdoc in Portugal, and I was playing volleyball a little too much, and I ruptured my Achilles tendon. And I had never really thought about how your body heals itself. I literally never thought about that because I never had any major injuries until that point. And I do physical therapy every day for 3 months. And so I'm making conversation with my physical therapist one day. And since I just started my postdoc, I was working on bone was my new tissue of interest, not cartilage anymore. And he's like, so what do you do? And I said, I'm trying to grow bone. And he was like, bone? Why do you want to grow bone when it heals itself perfectly without scarring? And I was like, I mean, it doesn't always heal itself perfectly, like if you get shot, when you should not talk about getting shot to a European who thinks that we just shoot each other all the time over here, So I really reinforce that stereotype of Americans. But the point is, yes, there are bone defects that do not heal themselves perfectly, but there's also times when they do heal itself perfectly. And so that conversation was extremely impactful for me because, one, it made me realize if you can't answer the question, why are you doing something, you probably shouldn't be doing it. And two, why does bone heal itself perfectly? And if we can figure that out, can we fix it in the situations when it doesn't heal itself perfectly? And if we can figure that out, can we apply those same strategies to other tissues that don't heal themselves perfectly, like a heart attack? So that's myocardial infarction. If that happens, your tissue dies and it doesn't recover very well. But your body clearly has this ability to recover. It's the same kind of building blocks all over your body. Can we cause regeneration simply by designing a biomaterial that harnesses the natural healing abilities of the body? Is everybody with me? Does that make sense? Okay, awesome. So when I started thinking about along these lines, that brought me directly to the inflammatory response. So what happens when you have an injury, including implantation of an implant like a biomaterial, and so shown here is bone, but this is true for any tissue in your entire body. Damage to the circulation caused by that injury causes the release of danger signals from these dying cells. And these danger signals, that's actually the scientific term for them. And the danger signals recruit immune cells. And the most important immune cell that they recruit is called the macrophage. Now, I had no idea what a macrophage was until I started learning about this, and I realized that they are major regulators of tissue repair. And without macrophages, you can't have healing. So macrophages come in, they try to degrade the material because it's this foreign thing in the body which they've evolved over millennia to try to eliminate. And oftentimes, they will seal off this foreign body with a fibrous capsule, that's what it's called, surrounding the material to isolate it from the rest of your body. And we know that this has evolved to protect us from foreign materials that somehow make their way into our tissue because ancient mummies from ancient Egypt have been found with spearheads in their side or otherwise things that somehow they got stabbed with and there's some shrapnel in there. But they lived fine until old age, which I guess in ancient Egypt was like 20. But they died of other causes because their body was able to isolate that thing and protect them from it forever until they died of natural causes years later. And so evolutionarily, the fact that your immune cells do this is a great thing, right? But it's a bad thing if you're trying to design a biomaterial that promotes integration and healing with the surrounding tissue. But the thing is, this doesn't always happen. It depends on interactions with the material and the immune cells. So the overarching question of my lab now is, why is it that sometimes when inflammation happens, sometimes you have this fibrous capsule that rejects the material, and other times you have complete healing? Because there are materials that have complete healing, like a total joint replacement. Does anyone know anyone who's had a total joint replacement? So it's like titanium gets implanted into your bone, which is kind of crazy I don't know who thought of that one. But that actually gets anchored pretty well into your tissue, and that's because the inflammation progresses towards that route where you have blood vessels and tissue ingrowth. So this is the question, why is it that sometimes you have tissue ingrowth and blood vessel growth, which is critical for healing, and other times you have basically rejection of the material? And how do we design biomaterials to cause the direction to go in that way instead of this way? So when you look into a little bit more detail into the process that controls that decision between it comes down to behavior of macrophages. So macrophages, like I said, are major regulator cells that regulate all these other tissues involved in healing. And so if you kill them, you definitely cannot have healing. But if you change their behavior, it changes healing. So those are the clues that we might be able to manipulate macrophages like puppets, and then they go on and tell all the other cells what to do. So importantly, in normal healing, macrophages exist on at least two very different states. And we call them M1 and M2 to differentiate them, to talk about how different they are. But it's actually the same cell type, and they can switch back and forth, which is pretty amazing. So these M1 cells are very, very pro-inflammatory, and they're destructive, and they are responsible for killing off bacteria. But these M2 cells are associated with healing. And so when I was first learning about this, I was reading that they were pro-healing and pro-angiogenic. And angiogenic means they stimulate the growth of new blood vessels, and that's what I really wanted to focus on because blood vessels are so critical for the healing of so many different tissues. So I thought, this is great, I'll just make a material that promotes that M2 phenotype, and it'll solve all my problems because they'll talk to the blood vessels, they'll talk to the other cells that are involved in causing tissue integration. Does that make sense to everyone? You're on board with the strategy? So I just wanted to figure out these M2 cells, how to promote them, okay? So just to get started, I decided to do a pretty quick experiment to study blood vessel growth in a lab setting, in vitro. Okay, so I was able to make these cells, I was able to force the different phenotypes, these different states of macrophages in the lab, and then I won't get into the details about how I did that, but established protocols. And then I took the signals that they were releasing and I added it to endothelial cells, which are the main cells of blood vessels, in an assay in which if they sprouted more and they branched more, that means that you have more potential for blood vessel growth. And if it's an anti-angiogenic or if it's an inhibitory process, they'll like shrivel up and they won't branch. Okay, so does everyone understand how the assay works? So the more branching, the more potential for blood vessel growth. Okay? So my hypothesis was that the M2 macrophages would cause the most branching because that was what the literature was suggesting. And I thought the M1 macrophages would inhibit that behavior because they are these destructive pro-inflammatory cells. So it turns out it was the exact opposite of what I just said. So the M2 macrophages actually inhibited blood vessel growth in this assay, which was extremely surprising, and I thought a major setback at the time because I was reading so many articles that were saying M1 macrophages were bad for blood vessels, M2 macrophages were good. And if you look, not only were the M2 macrophages bad, the M1 macrophages were good. So everything was wrong in this situation. And I thought I was doing something wrong. It was kind of a technically challenging assay, so I was kind of freaking out. But then I decided to just analyze what the cells were secreting, like in terms of proteins, because the proteins are what cells use to communicate between each other. So I thought that would give me some clues into how this could possibly be happening. So the first protein that I looked at was VEGF, or vascular endothelial growth factor, which is the most potent growth factor that we know of that promotes blood vessel growth. And shockingly, it was secreted by these M1 macrophages, even though all of these papers that I was reading was saying that it was M2 macrophages secreting them, and that M1 macrophages inhibited this process. So now I'm like, oh man, I'm going to publish this in Nature, this is going to be awesome, because this is really, like, this is a clear result that everyone's wrong. And I don't know why everyone's wrong, but this is like a very obvious result here, right? But then I realized, once I looked into the literature a little bit more, I was not the first one to have found this. It's actually very well known that inflammation leads to the growth of new blood vessels, because that's how you get healing to occur. That's how you bring in all these repair cells, and that's why every inflammatory disease that exists is associated with pathological blood vessels. So like diabetic nephropathy, macular degeneration, rheumatoid arthritis. All of these diseases have too many blood vessels and too much inflammation. So it doesn't even make sense that these M1 macrophages would be bad for inflammation. So how could everyone be so wrong? Well, then I looked for the second most important growth factor, which is PDGF. And PDGF is very important but very different from VEGF, because it acts at later stages of blood vessel growth. So whereas VEGF acts at early stages and is critical for initiating the process, if you don't have PDGF, all those blood vessels will eventually die and you won't have healing. So, and if you recall, I told you that M1 macrophages appear early in the healing process, and M2 macrophages appear later in the healing process. And M1 macrophages secrete proteins that act at early stages, and M2 macrophages secrete proteins that act at later stages. This suggests that they actually work together and sequentially and synergistically to promote blood vessel growth. So this is our theory right now, that M1 macrophages are there in the beginning to promote blood vessel growth, and M2 macrophages come later to stabilize it. And if this is true, this also explains why all these people thought that it was the M2 macrophages that were most important for blood vessels, because if you looked at later stages of healing, there's no way you would see blood vessels unless there were M2 macrophages there. You'd have to look at extremely early stages to recognize the importance of the M1 macrophages, and no one really does that because of just time and money. You just typically look at later stages. You'd have to look within one day to see the importance of the M1 macrophages. So this is very exciting, and this is something that we're exploring in a lot of detail in my lab now at Drexel. So Pamela Graney is a fabulous PhD student of mine who decided to go to a person's lab, Shulamit Levenberg, at the Technion Israel Institute of Technology, because Shulamit, Dr. Levenberg, had this really cool model of human blood vessels that she could grow in the lab. So she took human endothelial cells and human supporting cells that are important for causing the blood vessels to grow, and she combined them with the porous material, and then they spontaneously grow these beautiful blood vessels in the lab, in a petri dish, that are actually functional blood vessels. So you can hook them up to a pump, and you can pump blood through them, like they're hollow tubes, which is pretty cool. And so Pam decided to just add macrophages to this system in a controlled way to try to understand what is the contribution of these M1 and M2 macrophages to the process, to try to prove our hypothesis or disprove that sequential M1 and M2 macrophages are beneficial, because people are kind of skeptical about that idea, because for so long the dogma has been that M1 is bad and M2 is good. So these are pictures of the blood vessels growing in vitro. And so you can appreciate that the number of the branches is how many blood vessels you have. Although I guess it's a little bit hard to see with this lighting. But basically, when she sequentially added M1 and M2 macrophages, there was many more blood vessels than the controls with either M1 or M2 or no macrophages. So we really think that it makes sense too. So this is what we think, that M1 and M2 macrophages are working together, and Pam is finishing up her thesis this year to repeat these studies and make the controls more robust, and to really analyze what is exactly happening in the communication between these cells. Like, how do the macrophages communicate with blood vessels to do this? But this really influences the design of biomaterials, which is how I started this whole rabbit hole expedition, was how to make a biomaterial that promotes healing. And so what this suggests is that we want to make a biomaterial that first promotes M1 and then promotes M2. Because if you don't have both, you're not going to have optimal healing. And so I have a lot of students working in my lab on various aspects of this, on various applications. So Emily and Claire are talking in the 3MT competition later, so check them out. Amanda is in Korea right now working on rheumatoid arthritis, Kate's working on traumatic brain injury, Bhavani is helping her, and Greg is just starting to see if we have to invent novel methods to release drugs from scaffolds in order to do this. Okay, so in the interest of time, I'm going to go quickly through the stuff that we're doing with diabetic ulcers because I do think it's really exciting. So the way that I got into diabetic ulcers is completely happenstance in that when I first started at Drexel, there was some welcome dinner to new faculty, and I was seated next to Dr. Michael Weingarten, who's been leading the Drexel Chronic Wound Clinic for the last 35 years. So he's the chief of vascular surgery here. And he said, oh, you like inflammation, you should spend a day in my clinic and learn about diabetic ulcers. And I said, okay. So I didn't know anything about diabetic ulcers, but I definitely knew a little bit about diabetes. Does anyone know anyone in here with diabetes? Yes, everyone. It's an epidemic. So it turns out that people with diabetes often have these wounds that form on their lower extremities, especially their feet, and these wounds sometimes heal and sometimes they don't heal. And it's really not well understood why that happens, why sometimes they heal and sometimes they don't heal. So you can imagine how difficult it is to treat a patient with a diabetic ulcer if you don't even know why sometimes they heal and other times they don't heal. It's a lot of guesswork right now, which is, it's all based on empirical practice right now, but the science behind it is very poorly understood. So we know that diabetes is an epidemic, but there's some statistics about diabetic ulcers in particular that are staggering. So first of all, diabetes affects 30 million Americans right now, and 1.5 million patients have a diabetic foot ulcer every year. And it's expensive to treat that ulcer. It costs $20,000 per patient to treat an ulcer on top of what it already costs to treat a diabetic patient, which is already a lot of money. So that amounts to $30 billion annually in the US alone. And because a lot of these patients, most of the patients are on Medicare and Medicaid, we're bankrupting the American economy right now by not doing a better job treating diabetic ulcers. And if that is not enough reason for you to think that more people should be working on this, there's a 5-year mortality rate of up to 55%. So depending on the severity of the wound that you have, and if you have to get an amputation, you have a 55% chance of dying in 5 years. This is really a life or death situation. It's not just that we need a better Band-Aid. So if you have any parents or anyone who are pre-diabetic in the room like I do, tell them that this is serious and that they need to watch their glucose and don't get diabetes because it's a bad, bad problem. Okay, so maybe I have a little bit of time to go through this. No, I'm going to skip it. It's too much. I'm sorry. I was going to just do the same thing when I make an M1 to M2 promoted biomaterial. It seemed there was some previous literature suggesting that it should work in the human. It should work for diabetic wounds, but it had never been shown in humans. So we just wanted to confirm that it happened in humans. We tried to analyze it, and it was meaningless, the data that we got out of it, because there was so much heterogeneity. So this was a major setback that we couldn't understand any of the data. And that's the point of this figure right here, that it's not understandable. So if you don't understand it, that is exactly my point. We didn't understand it either. So what we had to do was invent a novel way to interpret the data just to make the data easier to interpret. So we took all of those pieces of data that I just showed you and combined it into a single score that was higher for an inflammatory M1 and lower for an anti-inflammatory or pro-healing M2, and just to make it easier to visualize the data. And we used this in normal wound healing, and we saw it spike after normal wound healing and then decrease, and which is what we know is supposed to happen in normal wound healing, as I already told you. But it was amazing when we applied it to human diabetic ulcers, the tissue collected from Dr. Weingarten's patients. There was this major stratification between patients who didn't heal and patients who did heal. And so it turned out in the pilot study, it was 100% accurate for predicting who would heal and who would not heal. And I knew from collaborating, because Dr. Weingarten has been collaborating with Drexel Biomedical Engineers for the past 10 years to try to invent a diagnostic to even tell if a wound is healing or not, because you can't even tell right now in clinical practice if it's healing. And so we accidentally invented a novel diagnostic that's 100% accurate for predicting healing or non-healing. Actually, on the follow-up, it's great. It's 90% accurate right now, which is actually a good thing because when you tell potential investors that it's 100% accurate, they think that you're either wrong or lying. So now it's a more reasonable number, which is 90% accurate. And so we are trying to commercialize this now because it has a lot of potential to really help treatment of patients with diabetic wounds. So the last thing that I wanted to talk about is some of the international collaborations that we're doing right now, because all of my students study abroad or do research abroad because it was so important. Oh, I just saw that next to Emily's face is the cat C. That's a coincidence. That's my name. Okay, anyway. So it was so important in my own education, not just personally, because you do have your personal growth, yada yada yada, you find your zen, but it actually made the science a lot better when I had these international collaborations as I went through with the Chinese collaboration. So I wanted to do an experiment on my students in which I determined if international collaboration would make their science better. And so these are some of my students that have gone to various countries around the world so far to try out different things. So I want to highlight a couple of them today that were particularly creative. But what is really, a study that just came out 2 years ago that I think really highlights what I'm talking about here is from economist in Columbia, Adam Galinsky. So it's called Fashion with a Foreign Flair, Professional Experiences Abroad Facilitate the Creative Innovations of Organizations. And so this study showed that French fashion, or not French, fashion designers from any country who went abroad and lived abroad, their work was objectively rated as more creative than other fashion designers' work, suggesting that it was the international experience that made them more creative. And that was certainly true for my own work, so that's why we're trying to figure that out here. And actually I'm collaborating with Dean Herbert to try to understand if this is something that also is true in biomedical engineering and psychology and other fields. And I'm also working with the Institute of International Education in Fulbright to see how we can quantify this behavior in people who have gone abroad to see if the same thing holds true. So Claire Witherall was my first student to go abroad. She actually first went to China and then later to the United Kingdom, to Bristol. And when she went to the UK, she was a Whitaker Fellow, which is a prestigious fellowship to go abroad. And what she decided to do was implant biomaterials in zebrafish. So zebrafish are a model organism that we use to study tissue regeneration because they regenerate tissues very well. And no one had ever implanted a biomaterial in a zebrafish, but if they have a regenerative response to biomaterials, they could be a really good way to study how to make a biomaterial with a regenerative response. Does that make sense? Yeah, it's a little bit crazy. But so what we're looking at here are little yellow microparticles inside that were injected into the fish, and you can see macrophages are labeled in red, and they're grabbing them and pulling them around the body and dealing with them in interesting ways. And so what Claire found with this study is that neutrophils, which are another immune cell, and macrophages cooperate to coordinate their response to biomaterials in zebrafish. So this could be really important because zebrafish allow you to do all these interesting experiments that are very cheap and very fast, so we could really accelerate our research by using this model. So Amanda is a PhD student that I advise with Yuri Gagotsi in material science here at Drexel, and she's currently in Seoul, Korea, on a Whitaker Fellowship and also a Boren Fellowship, which are both very prestigious. And she's looking into using nanodiamond, which is literally diamond on the that's nano size, but it turns out it has very rich surface chemistry, so she's loaded it with drugs to see if you could use that to modulate macrophage behavior for inflammatory diseases like arthritis. So she's currently in Korea, and it's going very well. Nathan is a BSMS student who is graduating this year with his bachelor's and his master's, but for his third co-op, he went over to my colleague's lab in Portugal and studied a way to use 3D printing to make cartilage, to then turn cartilage into bone in the body. Because that's actually how bone heals itself. A lot of people think that bone just spontaneously forms. It actually first forms relatively soft cartilage, and then it remodels it into bone. And so that is potentially a better way to repair bone than what we're using now in some of these catastrophic defects. And Emily, we're very excited about, just received a Fulbright Fellowship and a Whitaker Fellowship, which I've never met anyone who's gotten both, until now, so that's very exciting. And Emily made this collaboration herself with Caroline van Boon at the Eindhoven Institute of Technology in the Netherlands, And so Emily will be talking in the 3MT competition later today, so make sure you check it out. But basically, she's looking into heart valves. So a lot of children are born with a heart valve defect, and you can imagine that would be difficult to survive with a heart valve defect because your heart's kind of an important organ, and the heart valves are important for regulating blood flow. So Emily is looking into whether or not you can design synthetic heart valves so that they modulate the immune system in order to promote better healing so that you can have long-term functionality. Okay, so in conclusion, say yes and. And so my point with this is that if somebody presents you with a crazy idea, you need to be prepared to take risks. But by be prepared to take risks, I mean prepare yourself to take risks. It's not just going to happen. You need to first be willing to accept the risk, and then second, work to make sure that if you take a setback and turn it into an opportunity. And so that's the third one, turn setbacks into opportunities. So with that, I want to thank all of my collaborators and mentors here at Drexel and around the world, especially Dr. Weingarten, Dr. Lewin, and Dr. Niederauer here in Biomed introduced me to the importance of diagnostics and diabetic ulcers. Will Dampier has been really helping with a lot of the bioinformatic analysis that we were never taught as biomaterials engineers, but that's really important. I mentioned Yuri Gagotsi, and the other people are collaborating. I didn't mention the people who I highlighted in the slides for the sake of space. And I also really want to thank my lab because I have amazing students, and I think you probably realize that I couldn't do this without any of them because I'm not actually doing the experiments anymore. I'm just living vicariously through them as they do these really cool experiments. So I just want to thank them for all of their hard work and thank all of you for all your attention.